Okay, good morning everybody. In today's session, I will be discussing about series and parallel arrangement of closed coiled helical springs and some numerical examples on closed coiled springs. So here, first let us discuss one example. The problem reads like this. A hollow steel rod 200 mm long is to be used as a torsional spring. The ratio of inside and outside diameters of the tube of the rod are 1:2. The ratio is 1:2. The required stiffness of the spring is 100 Newton meter per degree. The required stiffness of the spring is 100 Newton meter per degree. Determine the outside diameter of the rod. The modulus of rigidity is 8 into 10 power 4 Newton per mm square. Okay. So here a hollow steel rod with internal diameter d1 and external diameter d2, which are in the ratio of 1:2. 1:2. So this rod is used as a spring whose stiffness is to be 100 Newton meter per degree. The stiffness is given as T by theta, angle of twist. Theta is angle of twist. So the stiffness is given as torque by theta, angle of twist. Okay, and this is given as 100 Newton meter per degree. It can also be expressed as Newton meter per radians, and the value of this in radians is to be found multiplying with 180 by pi. 180 by pi. Okay, 1 degree is 180 by pi radians. Pi by 180 radians. So it is in the denominator pi by 180 radians. Okay, so when this comes to numerator, it becomes 180 by pi. So 100 into 180 by pi Newton meter per radians. That is the value of stiffness expressed in Newton meter per radians. Okay, so we have to use this value in Newton meter per radians actually. So let us see how to solve this problem, how to find the diameters of the tube. So the length of rod is mentioned in the problem, it is 200 mm. When expressed in meters, it is 0.2 meters. And the ratio of inside to outside diameters is 1:2. And stiffness of spring 100 Newton meter per degree, or in Newton meter per radians, it is 5729.578 Newton meter per radians. Okay, and rigidity modulus is 8 into 10 power 4 Newton per mm square. And the same can be expressed as 8 into 10 power 4 into 10 power 6 Newton per meter square. We are converting mm square to meter square. So in the denominator, you will have -6. When it comes to numerator, becomes +6. Okay. So now, by using torsion equation, we know this relation. T by IP is G theta by M. That is torsion equation. Okay, where T is torque, J is polar moment of inertia, G is modulus of rigidity, theta is angle of twist, and L is the length of the rod. Okay. So from this we will obtain this T by theta equal to Gj by L, and we know the value of T by theta, which is nothing but stiffness. Okay, that is clear. So the diameters are in the ratio of 1 is to 2. Outer diameter is 2 times of inner diameter. And here G is given, L is given. So J, the polar moment of inertia, is found as pi by 32 into d power 4. This is for solid cross section. Okay. So for a hollow rod of outside and inside diameters d2 and d1, the polar moment of inertia is pi by 32 into d2 power 4 minus d1 power 4. Okay. And you know the relation between d2 and d. Okay. So this comes out to be pi by 32. When you replace d2 by 2d1, it becomes 16 d1 power 4 minus d1 power. So it becomes 15 d1 power 4 here. So 15 pi by 32 d1 power 4. That is the value of polar moment of inertia. So substituting these values in this equation. So the stiffness is, in terms of Newton meter per radian, 5729.58. And this is G, 8 into 10 power 4 into 10 power 6. Okay. Divided by L. G by L, and this is J value. So substituting all this, you will get D1, the diameter, inside diameter. Okay. Which is 9.93 into 10 power minus 3 meters. In millimeters, it is 9.93 millimeters. And outside diameter is 2 times of inside diameter, isn't it? 2d1. That is 19.86 millimeters. Okay. That's how we'll find out. The diameters. Okay. So that is the example. Now let us see the case of parallel and series connection of springs. Okay. Closed coiled helical springs when connected in series. Okay. Connected in series and connected in parallel. So this is the case of series connection of springs and parallel connection. So in case of series connection, number of springs with different stiffnesses are connected in series and a load is applied. Okay. In this case, each of this spring will be subjected to the same load P. Okay. Same load P. P or F. We use the letters P or F for denoting force. So here, let K1, K2 be the stiffnesses of two springs connected in series. So our this one is to find the stiffness of a single spring which can replace the given series of springs such that it satisfies the condition. What is the condition here? The elongation of the springs x, if total elongation of this assembly of springs is x, then it will be equal to x1 plus x2. Okay, where x1 is the elongation of spring 1 and x2 is the elongation of spring 2. Okay. So the total elongation of the spring is x1 plus x2. And the spring which replaces should have the same elongation x. So what will be the stiffness of the spring which can replace the given assembly such that the elongation is same as the series of springs connected in series. Okay, the elongation in the case of series of springs. So how to find the equivalent stiffness now of the spring which can replace these two, satisfying this condition. Okay, that is our problem. Same is the case with parallel connection, that we will discuss later. So here the springs are subjected, okay, K1, K2 are the stiffnesses we are calling, and F be the force acting on it, and X1, X2 be the individual displacements, extensions of the springs. So the total elongation of the assembly is sum of these two, X1 and X2. And we have seen each of the spring is subjected to a force F, same force F. Okay. So F is given as K1 X1. Okay, because the spring is of stiffness K1 undergoes a deformation of X1 when acted upon by force F. So the relation is F equal to K1 X1. Same is the case with the second spring K2 X2. Okay. Now X1 in terms of F and K. From this, X1 is F by K1 and X2 is F by K2. So what is the total elongation? X1 plus X2, that is F into F by K1 plus F by K2, or F into 1 by K1 plus 1 by K2. Isn't it? Now the spring which replaces this should have the same extension X under the force K. Under the force K. So if K equivalent is, or K equivalent or K effective is the stiffness of the spring which replaces, then K effective into the displacement is equal to F. This relation we use. Okay. So let us see that. Yeah. So if K effective or K equivalent, as we have discussed, F is equal to now K effective or K equivalent into X. We replace X now by F into 1 by K1 plus 1 by K2. This one. Okay. So here F gets cancelled. The K effective is 1 by sum of 1 by K1 plus 1 by K2. Isn't it? So this is the relation between the stiffnesses. The effective stiffness or equivalent stiffness is given as 1 by K1 plus 1 by K2. Or we can also express this as 1 by K effective equal to 1 by K1 plus 1 by K2. This is for two springs. We can generalize this. There are n number of springs. Then we can find the effective spring constant as the sum of the reciprocals of the stiffnesses. 1 by K effective equal to 1 by K1 plus 1 by K2 and so on up to 1 by Kn if there are n springs. Okay. So this formula gives the stiffness of equivalent spring which replaces the given series of springs. Okay. Yeah. Now let us see springs connected in parallel. Again, you consider the stiffnesses as K1 and K2 and subjected to a force P or F. Okay. And what is this? In this case, both springs undergo the same extension. The springs here are connected between two rigid plates. Okay. Yeah. Under the action of the force, either tensile or compressive, they both undergo the same extension, delta or x. Delta or x. We represent the elongation by delta or x. So, unlike series connection, where the total elongation is sum of the individual elongations, x equal to x1 plus x2, we have seen that. Yeah? But here, the elongation is same for both. Elongation is same for both. But we can observe here, the force applied here is shared between the springs. If there are n number of springs, this force P is shared between the springs, between or among the springs, in the ratio of their stiffnesses. In the ratio of their stiffnesses. The force is distributed among the springs in the ratio of their stiffnesses. So what can we say now here? The total force P or F is equal to F1 plus F2 and so on. If there are n number of springs, then it goes up to Fn. Okay? Isn't it? So what is F1? F1 is the force taken by spring 1. So from Hooke's law, we know this relation. F1 equal to K1 into X. Here X is same for all the springs which are in parallel connection. Okay. Similarly, F2 is the force taken by spring 2, which is given as K2 into X. And we know that F equal to F1 plus F2. That is K1X plus K2X. Or K1 plus K2 into X. Okay. Now, if K effective is the equivalent stiffness, then K effective into X equal to F. Okay. So, F is equal to K1 plus K2 into X. Now, K equivalent is the equivalent stiffness of the single spring which can replace the assembly of springs. Okay. So, with the relation we have F equal to K equivalent into X. So, you replace F here by K equivalent into X. Okay. K equivalent into X. So X gets cancelled and you will have K equivalent equal to K1 plus K2. So it just gives the equivalent stiffness or the sum of the stiffnesses of individual springs when they are connected in parallel. Okay. If there are n number of springs, we can generalize this as K1 plus K2 and so on up to Kn. Okay. When there are n number of springs connected in parallel, then we can find effective stiffness or equivalent stiffness simply by adding the stiffnesses of all the springs. Okay, yeah. That's how we'll find the effective stiffness of springs connected in parallel and in series. This is for series parallel connection. Okay, and what is it for series connection? We have seen just now. 1 by K equivalent. Okay, 1 by K equivalent is equal to 1 by K1 plus 1 by K2. and so on up to 1 by k. Okay, this is for series connection. This is for parallel connection. Is this clear? Okay. Now let us see one example. Consider the problem reads like this: two close coiled helical springs wound from the same wire but with different core radii have having equal number of coils are compressed between rigid plates at their ends. Okay. Calculate the maximum shear stress induced in each spring if the wire diameter is 10 mm for both the springs and the load applied between the rigid plates is 500 newtons. The core radii of the springs are 75 and 175 mm respectively. So you have two springs outside and inside. The core diameters are 75 and 100. Okay, two springs, one inside the other, are connected between two rigid plates. Two rigid plates. Okay, yeah, we have two springs connected, one inside the other. One inside the other. They both have the same number of coils. That is, number of coils in one outer spring and number of coils in the inner spring N2. They both are equal. Okay, number of coils are same. So they both are compressed between the two rigid plates. That means they both are subjected to some force F, which is 500 newtons given. Diameter of Y, it is small d. Same for both, inner and outer. Now, to find shear stress induced in each spring, tau, you need to find tau. For that, we use torsion equation. Okay, torsion equation we use. And before that, core radii is given for both 100 and 75 mm. So here the what you need to find shear stress you have to find. For that, first let us see what is the data given here. N1 is equal to N2, that is mentioned in the problem, and diameter of wire is 10 mm. W load 500 newtons. R1 and R2, the radii, not the diameter. This is 200 and this is 1. The radii are 75. These two are radii, not diameter. So diameters are 200 and 150. And we represent the radii by capital R. Okay. Tau, the shear stress, tau 1 and tau 2. The shear stresses induced in outer and inner springs. And coming to this load W, which is shared between the outer and inner springs, because these two springs are connected in parallel. So this comes under parallel connection of springs. Okay, in which the elongation or the compression is same for both the springs. Compression X is same.
Like, share and subscribe. Hit the bell icon for more updates.